Hello everyone. Sorry I had to be gone today and tomorrow, but I'm attending a conference in Philadelphia. As far as yesterday's homework assignment, what I'll do is I'll tell you to hang on to that, and then we will, I'll correct it and collect it. I'll go over it more on Monday. However, just so you can start to correct any mistakes or questions you might have, what I've done is I've given the sub a link to this file, but I'm also going to show it right now. So here is the answers to that worksheet from 8.6. So question 1 was yes, that is indeed an exponential. Its equation is y equals 1, that's the y-intercept, times 1/5 to the power of x, and the reason it's 1/5 is because they're decreasing. It's a decay. It's divided by 5 or multiplied by 1/5. In graph 3, you have a y-intercept of 1, and then it's being multiplied by 1/12. That's why it's decay. Zoom in a little bit. And then in 5, y-intercept is 1, because there's really a 1 out front, and then to get the other points, you have to use your decay of multiplied by 8/9. It's decay because it's less than 1. And 7, your y-intercept is a 2, but your growth factor is 1/5. It's decay because it's only getting 1/5 of its value, so I need to see your table for that, but there's what the general graph should look like. On Monday, I'll check to see your tables. Question 9, your y-intercept starts at 2, and you're only getting 25% back. Again, that's decay because you're getting back less than 100%. So you got to divide by 4 and multiply by 2.25. In question 11, your y-intercept is negative 0.2, and then again, you have decay because your growth factor is less than 1. You need to make a table to get a few more points. 12, 13, and 14, you were to graph those and then compare them. I've actually done so in Desmos right here. So here's 12, and then 13 in blue, and 14 in green. And I want you to look at these. One thing to note is they all have the same growth factors of 1/8. They're all decay. That means they go to 0 in the long run. As you can see, they approach 0 over here on the right. However, they start at different places, and that's what makes them different. The first one in number 12, it has a y-intercept of 2. That's why it grows a little bit. It's why it decays a little bit faster than the blue one. So it starts a little bit higher. The blue one, which is number 13, it has a y-intercept of negative 1. And then the green one, which is number 14, it has a y-intercept of 1/4. It starts right there. They all have the same growth factors, though. So they're the same in that they are all decaying at the same rate. They're different in what they started at, what their y-intercept was. So that was the takeaway for 12, 13, and 14. I still would like to see your tables for those as well when I come back and check on Monday. Okay, moving on then. You can correct yours, like I said, for yesterday's. Today's, what I want you to do is do the warm-up questions, but instead of doing them in the homework, I want you to do them on the whiteboard. So use your individual whiteboards. The first one I want you to do is I want you to graph y equals 8 times 1/2 to the x. That's a decay, so that's a review of what we were doing yesterday. The second one is a review of what we were doing 2 days ago. So in question 2, I want you to use this equation that we found over here on the right. It says your family bought a house for $150,000 in the year 2000, and we're going to call the year 2000 time t equals 0. And we want to know what the value, so this right here, this is time t equals 0. The value of the house increases at an annual rate of 8%. As a decimal, you need to know that that is 0.08. What is the value of the house after 5 years? So you're going to use this equation right here in number 2. Number 1, I would suggest making a table and then plotting out the points. So do both of these on your individual whiteboards. Pause the video now. Let's give everybody about 3 minutes to give it a chance. Come back in 3 minutes and we'll review it. So pause the video now, please. Okay, welcome back. Let's go over it. Very first one, the thing to pick out is to start, the y-intercept over here is 8. So at 0, y is equal to 8. The growth factor is 1/2, so I'm getting only half back. I'm dividing by 2 or multiplying by half. Here's going to be a 4, here's going to be a 2, here's going to be a 1. Over here, if I'm cutting in half going to the right, it means I must have been twice as big over here. This must have been a 16. So I have a table. I can plot out my points. I'm not going to be able to fit the 16 for y. I'm not going to be able to fit this point on my individual whiteboard, but I can plot the other ones. I have a y-intercept over here at 8. The next one is 1, 4, then 2, 2, then 3, 1. If you wanted to, you could say then 4 would be at a half, 5 would be at a quarter, 6 would be at an eighth. You get the idea. And it would end up looking like this. One thing to note is it is never going to touch that x-axis. Even if you keep cutting in half, you're never going to get a y of 0. So it looks like that. There's your graph for number 1. That's a review of what we were doing yesterday. Question 2 asks you to use my growth equation to determine the value of my house. So the first thing I need to know is A is my initial value. The initial value of the house is $150,000. So I'm going to say y is equal to $150,000 initially. It's growing. That's why I need 1 plus. It's growing at 8%, so I'm going to put 0.08 in there. If it's growing by 8%, really, when I simplify inside this parenthesis, I'm going to get 1.08. It's growing to 108%, and I need to put in the time. It was 5 years later. So once I've put in all my values, I can determine the value of the house. The first thing I do is I type in my calculator 1.08 to the power of 5. That gives me 1.47, which actually tells me that after 5 years, the value of my house is now grown by 47%. It is 47% more valuable. So I take 1.47, I multiply by $150,000, and at a very large growth rate, my house is now worth $220,500. And this was something that happened with house values in the early 2000s. They were growing at a very fast rate, and there was kind of a bubble that developed, and then that bubble kind of burst. But this was what was happening with the housing market, is that the values of houses were increasing significantly faster than the economy supported. But you can calculate it using math. So there we are. There's our 2 warm-up questions. Hopefully they went fine. Moving on to what we're going to look at today. Today we're going to look at a little bit of review of graphing like we just did, and then we're going to look at our growth rate functions. But over here, like we did in number 2, it's not going to be growth anymore. What we are going to look at is decay. So have your note packet open. It's 8.6 day 2, and the first thing we're going to do is we are going to compare some graphs. So what I want you to do is, I've shown them on the top of your note packet. I've got 3 graphs. Unfortunately, yours aren't color-coded, but I want you to match the exponential function with their graphs and explain how you know. So the first thing I'm going to look at is the y-intercept. I look at these. The y-intercept of this one is a 2. So y-intercept here is a 2. Same for this guy. Y-intercept is 2. The y-intercept for this one, there's a 1 out front. So the y-intercept for this last one is equal to 1. I know then actually right off the bat that the only one that has a y-intercept of 1 is the green one down here. So I actually know this has to be the green one. How else do I know? Well, its growth factor is 1.5. It's bigger than 1. It's actually the only one that's growing as well. Because it's the only one that's growing, I know that this must be the green one. The reason I know it's growing is because its growth factor B is greater than 1. Now I need to decide between this blue and the red. Well, the problem to start is that they're both decaying, and I can see that from their picture. They're both going downward. They're both getting smaller. Now I just need to look which one is getting smaller quicker. I can see that this red one is getting smaller quicker. Because it's getting smaller quicker, it means that this one must be the red one, and the reason why is because I lose so much more. This guy right here is multiplying by 0.2. That's a fifth. If I multiply by a fifth, I'm going to get a lot smaller faster than multiplying by 0.8. 0.8. If I multiply as a fraction is 4/5. That doesn't get me, doesn't decrease the size as quickly because it's 4/5. I'm getting 80% back. Here I'm only getting 20% back. So I know that the top one must be the red one because it has the smallest growth factor. It is dropping off the quickest. This blue one isn't dropping off as quick. It's getting 80% back, and this green one is the only one that's growing. So I know this top one is the red one, this middle one is the blue one, and this green one is the only one that's growing. So that's how you can reason through looking at graphs which ones might match which equations. Use y-intercepts, use growth factors, which one's growing, which one's decaying the quickest. Decaying the quickest is going to be your smallest growth factor. Okay? So things that we've noticed. We've noticed that if it's exponential growth, the big takeaway is that B is bigger than 1. You're getting back more than 100% of your value. If it's exponential decay, you're getting back between 0 and 100%. You're somewhere between 0 and 1. You need to be less than 1. You're getting less than 100% of your value. If I look at the pictures down here, this is exponential growth. The reason it's exponential growth is because B is greater than 1. You're getting back 150%. You're growing by 50% of your value for each interval of x. Over here, I see this is decay because your B, your growth factor, is less than 1. You're only getting back 80% of your value for each interval of x. So that's how I can tell the difference between growth and decay by looking at graphs and also looking at equations. What we're really looking at today, though, is the following. We're going to use our exponential. We did this as a growth model before. Now we're going to do it as a decay, and the reason it's decay is because of this guy right here. Is because we're doing a subtract now. I'm not getting back 100%. I'm getting back less than 100% of my value. You can also think of it as your growth rate now is really just negative. So there's a couple ways. You can either think of that as a negative, or you can just say it's subtract because we're getting back less than 100% of our value. Otherwise, it's the exact same that we were using 2 or 3 days ago. A is still your initial amount. Instead of plus, we're going to do subtract because we're going to be decaying. And we still have exponent of t because this is an exponential model. Things where this model is used is when things lose value. For example, cars lose value. So I can use this to find the value of cars. When you look up in Kelley Blue Book, they're using a version of a decay model. I can also use it when I'm metabolizing food, which is the example you do, or when you take medicine. Your body uses the medicine and it decays the amount exponentially. So we'll look at an example of that. To start, though, let's do a car depreciation one. So it says a car depreciates in value every year you own it. Suppose the car you want depreciates at 15% per year. How much is it worth after? Well, first we need to get a value of a car. So to start, let's look up a value of a car. So I'm going to go over here and get a new tab, and we're going to go to, let's say just a standard car. Let's do like a 2016 Chevy Malibu, just a very standard car. And they're telling me its suggested retail price is $21,625. Let's just call that $22,000 for sake of example. So $22,000 car. So to start, we know its initial is equal to $22,000, and that's important because that's our A right up here. How much is it worth after? Let's write T years to start. Let's do a general equation. So I'm going to go over here. I'm going to write my equation. It's going to be y equals, my initial value is 22,000. And then it's 100% of its value at the start, but it's losing, so I need to put subtract. It's losing 15%. 15% as a decimal is 0.15, and it's doing that for t years. And I'm gonna change t. Maybe it's 1 year, 5 year, or 10 years later. I'm going to simplify this just one more time. I get 22,000 is its initial value. 1 minus 0.15 is 0.85 to the t. This should make sense to you, and the reason this should make sense is because if you're losing 15%, it means the car is only worth 85% of its value each year. It's only 85% of its value compared to the prior year. So if you lose 15%, it means you're only 85%. So that's a key idea. Losing 15% is the same as saying only getting 85%. That means after 1 year, the value of the car is going to be 22,000 times 0.85 to the first power. I'm only getting back 85%. 85% of 22,000, if you're following along using your calculator, you get $18,700. That's the value after 1 year. 5 years, it would be, it's initially 22,000. It's only gotten back 85% of its value each year, and it's done that for 5 years. So I do 0.85 to the fifth power, multiply that by 22,000, and I now find the car is worth $9,761. After 10 years, I would say y is equal to 22,000 times 0.85 to the 10th power. I want to show this intermediate step here because there's something interesting. I'm going to do 22,000 on my calculator then. I'm going to type in 0.85 to the 10th power, and when I do that, I get 0.197 approximately, which really means after 10 years, it's only worth 19.7% of its initial value. It's only worth about 20% of its initial value. It's only 1/5 as valuable as it was initially. So when you show that intermediate step, you actually find out how valuable it is as a percent compared to the original. Now I take my 0.197 multiplied by 22,000 to find the current value of the car after 10 years. After 10 years, it's worth $4,334 after 10 years. This might be something that a person might want to know because maybe they think after a certain amount of time they might want to upgrade to a new car, and so you need to pay a down payment for a new car so that your loan rate isn't as high. And so you might say, I want to be able to put $4,000 down on a new car. And so if you bought a 2016 Chevy Malibu, you would say, if I can estimate its depreciation rate, I would say after owning it for 10 years, that's when I should be looking to maybe get another car so I can make a down payment on that other new car. So that's why people might be interested in doing a calculation like this. Your chance then to use this same idea in a different context. So on your whiteboards, last question of the day is a metabolism question. Your body metabolizes caffeine. That means it eats it up, caffeine at a rate of 14% per hour. So now your time just represents per hours. That's okay, so just know it's per hour. If you drink a cup of coffee containing 95 milligrams of caffeine, how much remains in your body after the following time periods? 1 hour, 5 hours, and I also want to know, can you set up the original equation right here? Can you pick out your initial amount? Can you pick out how much you're losing? And can you pick out your time period? So use our growth decay or our exponential decay equation to calculate how much body or how much caffeine is going to be left in your body after 1 hour, after 5 hours. And this would be important for a doctor. Doctors use this all the time with medicine. When they give people different medicines, they want to know how much remains in the body after certain periods before they can give them another dose. On your whiteboards, then try this. Take maybe 2 minutes, give everyone a chance to try it, compare with your neighbors, see if you're getting the same answers, and then after you're done pausing the video, press play to restart it, and I'll be happy to go over it. So press pause now. Okay, welcome back. Let's go over it. Set up your original equation. You'd say the caffeine in your body initially was 95 milligrams. I'm losing, so 1 minus 0.14, that's what 14% is for every hour. I'm going to simplify that. I'm going to move these down just a little bit, give myself a little bit extra space. Okay. So it'd say y equals 95 milligrams. 1 minus 0.84 is 0.86, which should make sense. If you're losing 14%, it means there's only 86% that remains left in your body every hour compared to the prior hour. So after 1 hour, I would say y equals 95 milligrams initially, only getting back 86% for 1 hour. So I do 0.86 to the first power is 0.86 times 95. I get 81.7 milligrams. So still quite a bit of caffeine left in your body after 1 hour. After 5 hours, I do 0.86 to the fifth power, and 0.86 to the fifth power turns out to be 0.47, so I'm going to do 95 times 0.47, which still means even after 5 hours, there's still 47% of the original caffeine left in your body. 47% of 95 turns out to be 44.65 milligrams still of caffeine left in your body. So your body doesn't eat out caffeine maybe as quickly as you might think. That's the main ideas for today. Hopefully that went over well. If you have any questions, you can ask when I come back on Monday. That means then for the rest of today, we are working on day 9 in our assignment sheets. You should know what questions those are. They're in the book. As you're working, it's on page 535. Answers to it are right here. Let's see if I can get the other document up. It's right here. So if you want to pause the video now and just leave this up so you can compare answers, feel free. I've also posted these to my website like I've done every assignment before. So you compare your answers to these ones. If you're graphing, you're going to need graph paper. Graph paper is over by the sink underneath the paper towels. I will ask to see your graphs though as you graph these. So make sure you can graph decay equations and then also set up some of these word problems that we've done. Okay. As far as tomorrow goes, there'll be the in-book assignment. There will also be a supplementary worksheet, just a few extra graphs for you, because that's the main idea of this chapter is graphing exponentials. And then also tomorrow might be a good day that if you finish early, make sure you have all your work in from the week. If you didn't quite complete an assignment, Friday, tomorrow's going to be a great day for you to be working independently, making sure you've completed all assignments. That means on Monday we will have our quiz over sections 8.5 and 8.6. Can you graph exponential growth and exponential decay equations and do some of those word problems like we've done with investments or decay? Okay, I hope you have a good day, and I look forward to seeing you soon.